Just give me a minute, I'll share my screen. So, okay, so let me know if you can see the screen.
Yes, I can see the screen.
Yeah, this is number systems. Um, so, the common number systems that we look at from any machine perspective or any system perspective is there are different bases: decimal number system, binary, octal, and hexadecimal. Decimal system has a base of 10, binary has a base of 2, octal has a base of 8, and hexadecimal has a base of 16. So we, for Verilog design, we would end up using decimal. Mostly it's binary or hexadecimal. Sometimes we'll use decimal numbers. So ultimately on a FPGA or a ASIC, everything is binary. It's 0 or 1. But when the numbers are very long, like 32 bits or more than 32 bits, like 64 bits, we end up using hexadecimal numbers, because looking at a 32-bit binary number will be very difficult. So it's easier to look at hexadecimal numbers and work with them. So finally, we end up working with binary and hexadecimal. But we'll see binary, decimal, and hexadecimal. Octal nobody really uses anymore, so we will not look at that in detail. Uh, a decimal system, as you know, it's a regular number system, 0 onwards. Uh, let's say 0 to 15 when we consider this 4 bits. Uh, Hexadecimal, if you can consider the equivalent of decimal, from 0 to 9, it's the same number for hexadecimal. 10 onwards, it changes. 10 decimal will be capital, A in hexadecimal. 11 will be B in hexadecimal. 12 in decimal will be C in hexadecimal. So on, D, E, F up to 15. Now, if you look at binary system, it has a base of 2. So 0 is actually, if you consider 4 bits, it's all 0 0 0 0. 1 is 0 0 0 1. 0 0 1 0. So 2 is 0 0 1 0. How is it that each has a base of 2? So 2 raised to 0, 2 raised to 1. This LSB bit on the right hand side has a weightage of 2 raised to 0. This is 2 raised to 1. Next one is 2 raised to 2. Next one is 2 raised to 3. Anything into 0 is 0. 2 raised to 1 is 2. So 1 into 2 raised to 1. 1 into 2 is 2. So it will give me 2 in decimal system. 1 1 binary will give me 3. 2 raised to 0, 2 raised to 1. 1 into 2 raised to 0. Anything raised to 0 will be 1. So 1 into 1 will be 1 for the LSB bit. Next bit weightage is 2 raised to 1, which is 2. 1 into 2 is 2. I add both this results. So 2 plus 1 will give me 3. 4 will be binary 1 0 0. 2 raised to 0, 2 raised to 1, 2 raised to 2. 2 raised to 2 will be 4. 4 into 1 is 4. Rest are 0 weightages. Phi is, decimal phi is 101. 2 raised to 0, 2 raised to 1, 2 raised to 2. 2 raised to 2 is 4. 4 into 1 is 4. Anything raised to 0 is 1. 1 into 1 is 1. So 4 plus 1 will give me 5. 6 is 110. 2 raised to 0, 2 raised to 1, 2 raised to 2. 2 raised to 2 is 4, 2 raised to 1 is 2, 4 plus 2 will give me 6. 7 is 111. So if we continue up to 15, it will be 1111. 8421 system, that's what we call it in binary. 8421 means 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. If you convert it to decimal, it's 8421 system. So 15 will be, all 4 bits will be 1. 2 raised to 0 is 1, 2 raised to 2 is 4, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 cube is 8, 8 plus 4 plus 2 plus 1, 12 plus 2, 14 plus 1, 15, I'll get 15 decimal. So 0 to 15 decimal will be represented as these numbers in binary and hexadecimals respectively. If we go for bigger numbers, decimal 16 for example, if you convert it to decimal, hexadecimal, the base is 16. So this is 16 raised to 0, 16 raised to 1. Anything into 0 is 0. 16 raised to 1 is 16. 16 into 1 is 16. So it will give me decimal 16. 17 will be hexadecimal 11. 16 raised to 0, 16 raised to 1. Anything raised to 0 is 1. 1 into 1 is 1. 16 raised to 1, 16. 16 plus 1, 17. 18 will be 12 hexadecimal, so on and so forth. In case of binary, if I look at 16, 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. This is the weightage for 1. 2 raised to 4 is 16. 16 into 1 will give me 16. Decimal. 17 will be, these are 5 bits now. 1, 0, 0, 0, 1. 2 raised to 0. This weightage is 2 raised to 0. This weightage is 2 raised to 4. Anything raised to 0 is 1. 1 into 1 is 1. 2 raised to 4 is 16. Into 1, 16. 16 plus 1, 17. Decimal. This is how the binary numbers work for decimal and hexadecimal numbers. Okay, any questions regarding this part?
No.
So obviously we can convert across bases or across systems. Any decimal number can be converted to hexadecimal or back to decimal. Any decimal number can be converted to binary. So between all the number systems, we can convert between each other. And there is a process to do that. So for example, 25 raised to 10, base 10. Base 10 means a decimal system. Will be represented as 11001 in binary or 19 in hexadecimal form. So when you look at the small numbers, you can manually calculate these numbers. But when you look at bigger numbers, you have to know the process how to calculate. So 125, if I have in decimal system, 125, how it works out, 10 raised to 0, 10 raised to 1, 10 raised to 2. So 5, 10 raised to 1 is 10, 10 into 2 is 20, 10 raised to 2 is 100, into 1 is 100, 100 plus 20 plus 5. 125 is my decimal number. So if I want to convert a binary number to a decimal number, so this is a longer binary number. So it's not that easy to convert manually just by manual calculation. So we have to follow a process for that. How do we do that? From LSB side, this is the weightage that we add, and we multiply it by that weightage, and finally we add up all of that will give me decimal number 43 in this case. Octal will skip hexadecimal to decimal. So now ABC is represented in hexadecimal format. If I want to convert it to an equivalent decimal number, how do I do that? This C is weightage is 16 raised to 0. This weightage is 16 raised to 1. This is raised to 2. C into 16 raised to 0. B into 16 raised to 1. A into 16 raised 16 square basically. A in decimal is, A in hexadecimal is 10 in decimal. B in hexadecimal is 11 in decimal. C is 12. So 12 into anything raised to 0 is 1. 11 into 16 raised to 1 is 16. 10 into 16 square is 256. You add up all this will give me decimal number for ABC. Equivalent decimal number for ABC in hexadecimal. Okay.
Okay.
Any questions here?
No.
From decimal, I can go to binary. How do I do that? So if I want to convert 125 in decimal to equivalent binary format, which has a base of 2, how do I do that? I keep dividing by 2 this number till I reach a stage where I cannot divide by 2. So 125 by 2, quotient is 62, remainder is 1. 62 by 2, quotient is 31, remainder is 0. 31 by 2, quotient is 15, remainder is 1. I keep dividing till I reach a stage 1 by 2, I cannot divide. So 0 is quotient, remainder is 1. When quotient is 0 means I cannot further divide the number. So this is my final binary number. So how is it represented? The topmost one becomes my LSB. The bottommost number becomes my MSB in binary. 1, 2, 3, 4, 5, 6, 7. This is a 7-bit number. The topmost number becomes my LSB, and this or 0th bit, the bottommost number becomes my MSB, which is 6 down to 0. This is how 125 in decimal will be represented as 1111101 in binary. Okay.
Okay.
So any big number also you can divide. I mean, obviously you have your own You can use a calculator or you can use an inbuilt calculator in a PC. But if you want to do it manually, you can do it this way. You check in certain cases. Octal can be converted to binary. We will not look at octal numbers. Hexadecimal can be converted to binary. This is relatively easy. Now this is 10AF is represented in hexadecimal format. How do I represent this in equivalent binary format? Each of this hexadecimal number is represented by 4-bit binary. Why 4-bit binary? Because hexadecimal, one hexadecimal digit can go from 0 to F. F means 1111, 15. So each hexadecimal number can be represented by 4 bits of binary. 1 is 0001, 0 is 0000. A is 10, so 1010. 8 plus 2, 10, binary. F is 15, 111. 10AF hexadecimal will be represented in the 16-bit equivalent binary. Okay.
Okay.
Any questions?
No.
Can I give you a small assignment task to do to convert a number?
Yeah, sure.
Okay, so take 100 decimal. 100 decimal, I want you to convert in equivalent hexadecimal number.
That'll be 64.
Will be 64 hexadecimal in hexadecimal, right?
Yes.
So 100 decimal will be 64 in hexadecimal. Now, if you want to
Yes.
convert the same in binary 8-bit number, what will be that?
No. 64. You have to keep dividing 64 by 2 and then you will get the number will be
Now you're trying to convert 100 decimal to binary or 64 hexadecimal to binary.
you just have to take the hexa number of 6 and hexa number of 4 that will be equivalent to binary.
Yes, you can
Just
do
like
that.
we have like
You can do that.
yeah, just like we have it on the screen 1 and 0. For 6 it will be uh, 0 1 1 0, and for 4 it will be 0 0 1 0 0 0 0 1 0 0.
Right. So equivalent binary will be 0110 0100. Right?
Yes, right.
Okay. So now one more small task is you convert 255 decimal to equivalent binary.
250. That will be 8 ones if you just divide it by 2.
Right. So all 11111111.
1 1 1 1. Yes, right.
Okay. So you got the idea, right? Converting one format to
Yeah,
another.
yes.
Okay. Any other questions regarding this?
Uh, no.
So yeah, when you convert decimal to hexadecimal, you insert when you convert decimal to binary, you divide by 2. When you convert decimal to hexadecimal, you divide by 16. And you get a stage where you cannot further divide by 16, and then you get the equivalent hexadecimal in that case.
Mhm.
Again, the right hand side goes to LSB, the topmost side goes to right hand side, which is LSB. The bottommost goes to left hand side, which is MSB. So this 13 is D, so 4D2 is hexadecimal equivalent of 1234 in decimal format in this case, this example. Okay, and binary also we can go from any number to any number.
Mhm.
Binary to hexadecimal is the reverse. From right hand side, we keep grouping the bits by 4. So this 4 bits will be whatever the value is, this under 4 bits. The remaining, if there are only 2 bits in this case, the other 2 bits, it has to be group of 4 bits. So the other 2 bits will be 0. We buffer it with 0. So 1011 is in binary. What's the equivalent? Hexadecimal. So you represent this 1011, it goes here. The next 4 bits 1011 goes here. The next 2 bits 10 comes here. But it has to be group of 4 bits for in to be represented in hexadecimal format. These are only 2 bits in the group on the MSP side. So what we do is I add another 2 bits which are 00 in that case. The number won't change. So 1011 is B, 1011 is B, which is 11 basically. So B 10 or 0010 is 2. So 2BB is hexadecimal equivalent of this binary.
Okay.
Anytime you have less than 4 bits, the rest of the bits you buffer them with zeros.
Okay.
It has to be group of 4 bits all the time. Okay, so that's how binary got converted to hexadecimal. Octal we'll skip. Hexadecimal to octal also we'll skip. Yeah, so that's the end of the number system overview. Any questions?
Okay. No.
Okay. In that case, I will do the FPGA design part also, FPGA fundamentals part also.
Okay.
So I'll just quickly go through the various fundamentals of FPGA design and where your Verilog comes into picture. FPGA or ASIC basically. So semiconductor overview, and then we will look at where Verilog comes into the bigger picture, and then we'll start looking at Verilog as a language.
Mm-hmm.
So as you know, we have semiconductors, which basically chips are made of semiconductors. So we have semiconductors everywhere in all kinds of applications. It could be computing applications, it could be telephony related application, automotive space. We have a lot of semiconductors. Avionics has is a huge market for semiconductors, and any other basically practically any other application you look at it today, you have semiconductor chips everywhere. So what is the overall logistics flow for a chip? This is a place where you are designing a chip or an integrated circuit. To design an integrated circuit, you need a lot of things. Uh, Design services. So this is where engineering people or engineers are hired as part of design teams, which will be part of the group doing the design. One thing you have to remember is not everything nowadays chips are not developed from scratch by so not all of the chip is developed by that team, because if you see the market today, you have to launch new products in the market. Let's take a smartphone industry. You have to launch at least two new phones every year. Apart from Apple, everybody does that. Apple also does it maybe a couple of years. So you have to launch a product in the market every quite often. You have to launch a product. For that, you have to design your product has to be. Uh, I mean, the new version of the product has to be engineered. So if you design it from scratch, it will take a very long time. You cannot launch a product in 6 months or 1 year's time. So that is where IP cores on the libraries come in. IP cores are basically called intellectual property codes. So these are like small designs done by some other company, and they are developed by some other company and sold or licensed to some other company to be used in their designs. Okay, so let's say Intel, no, sorry, not Intel. Some company, let's say X company is developing a chip, and within the chip there are multiple blocks, obviously multiple bigger blocks within the chip. If you do everything by yourself, your team does everything by themselves, it will take, let's say, 1.5, 2 years to develop the chip. But let's say there are five blocks in my design, my main five blocks in the chip. I take couple of blocks and either I outsource them or I purchase the source code for that block from some other company. That's what licensing does. Licensing an IP code does. So the other company is developing that block and selling company X the source code for that block, which will then get integrated in the rest of the design for company X. That way you save time on the design aspect. When you save time on one of the blocks, you save time on the entire chip. That is how a new chip can be launched in less amount of time. Do you understand this concept of IP code?
Yeah.
So there are design services which are basically engineering teams. You need IP cores. Normally, a lot of IP cores are used in the design nowadays, which are licensed from one external company or multiple external companies, depending on what the requirement is. Sometimes some companies will license the entire library of IP cores. So there are libraries of such IP cores which are developed by other companies and get licensed to some other companies who want to use them. There is a lot of software that goes into the design of a hardware integrated circuit. Depending on what your application is, there could be a OS involved in this. Then there are various other softwares called EDA tools, electronic design automation tools, which are used to perform verification of designs, to perform something called synthesis of designs, placement and routing of chips. All of those tools are packaged or grouped under EDA tools, which are with the full form for that is electronic design automation. You might have heard about company like Synopsys, Cadence, Mentor Graphics, or Siemens now.
I've used Cadence.
Cadence, which software have you used? Which
Yeah, I've used
platform?
Cadence.
Which RTL
I've
Encounter platform or which Incisive?
I've used Cadence for one of my course curriculums, RF integrated circuits.
RF. So it was
It was from
Virtuoso.
uh, it was to build schematics.
Oh yeah, what was the name of the software? Virtuoso or something else?
Yeah, yeah, Virtuoso.
Virtuoso. Okay. So you know that these companies will develop software. So Cadence is actually a software company who sells software to do chip design. Okay. So that's the contradicting part, but that's how it works. The entire chip design is extremely complex process. So it is next to impossible to do it manually. So you have to take help of softwares, which are called EDA tools. Normally, if you group all of them together, electronic design automation tools. So Cadence will sell different tools for different steps or different processes. Synopsys will sell different tools, or Mentor Graphics will sell different tools. And depending on what you have, you use them to do or carry out various processes or various steps of integrated circuit design. So, using all of this, all the knowledge, individual engineering knowledge, IP cores, software, any OS related information, using all of this, integrated circuit will be designed. Then that integrated circuit will be sent to system manufacturers who will then integrate or use that IC on their boards in their products. So the boards will be designed, the entire product will be designed, and finally the product will be launched into the market for the end consumer. That's the whole logistics flow for any integrated circuit, right? From design to the market. Okay.
Yeah.
And this is true whether you have a FPGA, whether you have a ASIC, whether even ASIC, any target technology, doesn't matter. People have to follow this. Basically, they will have to use all these different steps and various help available to get the chip out in time, and then the system manufacturer gets the system or the product out in time to the end market. So we'll do a small FPGA overview. What is an FPGA? FPGA stands for Field Programmable Gate Array. That's the full form. What it is, it's basically like a blank slate given to you to design your digital hardware system. You can build any logic, any kind of digital circuit on a FPGA. Only digital circuits. Now, we still don't have analog FPGAs where we can build analog circuits. Any circuit that goes on an FPGA has to be a digital circuit. Then we also have other chips called microprocessors or rather microcontrollers nowadays, which has internal microprocessor in them. A way a microcontroller works is it will execute basically a fixed program. It's a C program or an assembly language program that will be executed by a microcontroller sequentially, one after another. Internally, inside the microcontroller, you have fixed hardware and interconnections. There are memories, there are ADC, DAC components, there are timers, there are UARTs and other blocks inside the microcontroller. But all of that is fixed. It is given to you as a designer. You can either use it or not use it. In case of a FPGA, it's all blank. You can design whatever you wish. Nothing is fixed inside the FPGA. Everything is blank. You can develop a Verilog code to design any application. In microcontroller, you can design various applications, but you have to use the internal architecture, as we call it. Internal architecture of the microcontroller is fixed. You cannot change it. So you can use whatever is given to you, or you can let it go. That's how a microcontroller is different than FPGA. Then you have full custom or semi-custom which is called ASICs, application specific IC design. Application specific IC design also falls under two categories, subcategories: full custom ASIC, semi-custom ASIC. Full custom ASIC or full custom IC design, as we call it, the design will be done at CMOS transistor level. So it's extremely complex full custom IC design, and people work at a CMOS transistor levels. where you do all kinds of whatever you learned, characterizations, VI characteristics, IV characteristics, power characteristics, all that is done at a CMOS level, and then it is built up from the CMOS level. So it will take a lot of time. Then we have something called semi-custom IC design, where designers work at something called standard cell libraries. Standard cell libraries are basically logic gates, library of logic gates, which is one level of abstraction above CMOS level. CMOS level is the bottommost level on the IC. One level above is logic gates level, which is the semi-custom IC level. And then microcontroller and FPGA stands one level above. When you for FPGA you do design in Verilog, for microcontroller you do design in C language, embedded C language. So that's one level above, abstraction level above the other two levels, full custom and semi-customized. The category called PLD, programmable logic devices, is where you have FPGAs placed in. Complex PLD is a small FPGA. A normal FPGA is a bigger version of CPLD. So PLD is where the FPGA comes in. And normally the microcontroller is also clubbed under the PLD category nowadays because it's a programmable chip using a language. So PLD is where FPGAs and microcontrollers fall under. If you look at a system, FPGA based system, this is a FPGA based card that you can buy or you can build your own card. And it has an interface to your PC, normally through a USB interface. So on your laptop or your desktop, you can run FPGA software, various FPGA software through the cable and this interface. It will communicate with the FPGA on this board and vice versa, back and forth. So it could be as simple as this. Obviously, it's a very simple version of this. Or you can have this FPGA board. If you see this FPGA board, this is probably a PCI interface, which can sit on the motherboard of a desktop or a server. So this FPGA board can be part of the motherboard on a server somewhere, and you can access that server over a local Ethernet connection. So that could also be, that is how also it could work, this whole system concept. But it could be as simple as this. Nowadays, you get a lot of different FPGA kits which you can buy directly from the market. They will have this simple USB interface where it will be connected through to the PC through a USB interface. You can program the FPGA chip through this interface, or you can debug the FPGA chip using this interface. Okay.
Okay.
So you have to decide when to use a ASIC chip and when to use a FPGA chip. Normally, any such decisions, one of the major criteria is the finance or the economics of the product. FPGA, the few advantages that FPGA has, that it has the shortest time to market. You can launch the product, FPGA based product in the market very short amount of time compared to ASIC design. One of the main reasons for that is the lowest NRE cost, or the engineering effort required for FPGA is lesser compared to engineering effort required for ASIC design. Because for ASIC you have, sometimes you'll work at CMOS transistor level or logic gates level, and it will take a very long time to develop a ASIC. Whereas FPGAs can be developed relatively quickly because the design happens at Verilog language. ASIC also you can use Verilog and VHDL. It's not that we cannot use it, but at the end of the day, the steps required and the time required to develop a ASIC is more compared to the time required and the steps required to develop a FPGA. So it has the shortest time to market and the lowest NRE cost. NRE stands for non-recurrent engineering. It's a one-time engineering cost to develop a chip. But it has the highest unit cost. So if you develop, let's say, you manufacture, let's say, 1 million chips of FPGA and 1 million chips of ASIC. ASIC per the cost per chip for ASIC will be lower compared to cost per FPGA. Earlier, many years ago, the difference was very high. Nowadays, the difference has gone down drastically. So, the difference between a chip, ASIC chip per cost ASIC chip and per cost FPGA chip will be, still FPGA is costing higher, but the difference has gone down. So it's very close to each other. Earlier, what people used to do was teams or companies used to develop products using FPGAs, launch it in the market. Once customer get used to it, then you can develop a ASIC equivalent ASIC for it and try to reduce the cost of the product or improve your profit margins by developing ASIC. Nowadays, FPGAs are also used in full-fledged products, and people keep using them. You don't have to convert it to ASIC every time. Sometimes still they do it, but not every time. So this was cost related. The other reason that FPGA could be chosen over ASIC design is architecture driven. So if you have to develop a FFT for digital design, FFT is a fast Fourier transform using digital signal processing application. So depending on the kind of applications you're developing, you might need arithmetic operations on the FPGA like FFTs, multiplications, we call it MAC units, multiplication and addition units, which are again used for developing Fourier transform, cosine transforms, or other parts of signal processing. But there could be other areas where a FPGA will give you better performance compared to ASICs because FPGA has a lot of parallel logic. You can develop a lot of parallel logic in the FPGA compared to ASIC design. FPGA having parallel logic and having these other advantages like shortest time to market can then become advantages for the product design. One disadvantage with FPGA is it has no area control. Means FPGA chip, let's say it supports up to 5 million gates. Those 5 million gates are available to you. If you don't use the entire FPGA, whatever part you don't use will go waste. ASIC doesn't work that way. Application specific IC or ASIC is you first design the ASIC, you get the area requirement, then you manufacture it only for that area. So the area there is a area control over the chip. You don't waste the area on the chip. Whereas in case of FPGA, if you don't use the entire chip, if your design is not big enough and some part of the chip is empty, then that part is lost from an area perspective. So power control, power dissipation or power consumption is a very big topic now. People want to develop low power chips or chips which consume less power. In a case of FPGAs, earlier there was hardly any power control you could have over your design. Nowadays we have power control tools. So if you use Virtuoso, you might have done power analysis of your design. Right?
Yeah.
So
Uh, I've only developed like low power LPA, low power
okay,
and some mixer circuits for
okay,
my project.
okay. So in that case, you might have done a power analysis in Virtuoso, right?
Yeah.
So typically, if you know any total power consumption will be divided into static power and dynamic power. Right? Static power is related to leakage power, which you cannot really control. Dynamic power is related to your design and design frequency, design voltage, and some other factors, leakage factors like capacitance and other things. But operating voltage, operating frequency, and the logic of your design is factored into dynamic power calculations. So those things are nowadays supported by FPGA design tools, where you can also do analysis of your design. After placement and routing of your FPGA, you can run a power analysis on the design. It will generate a power report for you, and you can analyze the report for where the power consumption is. ASICs is all this power control was always there because it was required to do a power analysis and any corrections required before we went further. But with FPGAs now this is available as a part of the tool set. So this was FPGA related. Semi-custom IC design, as we said, are working with logic cells or standard cell libraries. Standard cell or standard logic cells or gates, and all the design is based or implemented using those standard gates in the library. So I will not go into details of this. Just Full custom IC design is where you have normally a mixed IC design. So digital and analog part both are required or is present. Analog part is where your RF will come into picture. So any analog part or any mixed signal IC design, normally people have to do some work at CMOS level, and when you have to work at a CMOS transistor level, that is where you do full custom IC design. So customization of transistor parameter characteristics basically is what is carried out as per your requirements, and they are fine tuned till you get the required characteristics out of them. So all that will be done using manual. So you have to you need a lot of, first of all, engineering effort to do that. You need a lot of tools to do that. So it will cost a lot of money to do that, and to do all of that will take a lot of time. So if there is really a requirement to do full custom IC design, people do it. Otherwise, they will skip doing full custom IC design, right? So that's how full custom IC design works. When
Okay.
you compare of certain parameters, time to market, volume, production, and performance, FPGAs are the best from time to market perspective. Volume means the cost, volume cost, or the cost per chip is less is basically higher. The cost is higher compared to semi-custom or full custom IC design. Performance is somewhere there. Semi-custom IC design is like the middle of the road. It doesn't give you a lot of advantages either way. Full custom IC design time to market is the worst. Means it will take a very long time to design the chip, and so ultimately it will take more time to launch the chip in the market. But from a cost perspective per chip and the performance, it's the best. The cost will be the least. The lowest cost per chip will be under full custom IC design. So you will do Apple does a lot of full custom IC design. Why? Because people want performance. They are selling Apple products are sold for their quality. That's why they charge twice or thrice the cost compared to other products in the market. So they are trying to sell their product based on quality. For quality, they will fine tune their product. It could be a smartphone or an iPod or whatever. They will try to fine tune their product or internal chip design in such a way that it gives you the best performance. To do that, they have to use full custom IC design techniques, which will give you the best performance. And such performance, you will do that only when you have to sell millions and millions of such devices or millions and millions of chips. When you manufacture in very high volume, the cost per chip will go down. So it's the best cost per chip and the best performance when it comes to full custom design. But time to market will be very long. It will take very long time to design the chip and launch it. That's why Apple doesn't launch a new product or a new smartphone before 2 years. That's what their time frame is. Right? Every 2 years they will launch a new smartphone, typically speaking. Nowadays, FPGAs and semi-custom FPGAs are replacing a lot of semi-custom ASIC devices or a semi-custom ASIC slots, or as they call it. So FPGAs will give you extremely good time to market. So quickest time to market, volume cost, and the performance is same along the lines of semi-custom IC design. So semi-custom IC design, nobody really does. Very less number of projects are done on a semi-custom ASIC nowadays. Either people go for full custom ASIC or they will transition to FPGA, the bigger size FPGAs, the latest FPGAs, which will give you almost everything that a semi-custom ASIC will give. Okay, so those are the things that people look at when you start a project, whether I use a FPGA or ASIC or how do I go about it. These are the three parameters to look at when you start your project. These are various application areas or the various industries where FPGAs are used. If you see military and defense, a lot of FPGAs are used. Aerospace, avionics, a lot of FPGAs are used. Telecom, so routers, switches, modems, a lot of FPGAs are used. Automotive is picking up. Automotive is mostly embedded domain where microcontrollers is used maximum. But FPGAs or lower size, the lower CPLDs, which are basically smaller FPGAs, are catching up in this domain. Industrial is industrial automation. This is where it's basically still a PLC domain, programmable logic controller, many years ago. So right now, it's that's how it's done. I mean, using PLCs. So FPGAs are hardly used. When you look at FPGA design companies, this is the market share. Xilinx is number one still. This is an old slide, but Xilinx is still number one. Altera was acquired by Intel, so this is number two is Intel now. Intel FPGAs is number two. Lattice semiconductor is still in the market. Lattice semiconductor, people use it for low power applications, low power FPGAs, and they are the cheapest of the FPGAs. So that's where Lattice comes into picture. Actel was acquired by Microsemi a few years ago, so Actel is nowadays Microsemi. The other players are very small. They are still there. Quick Logic is still there. Cypress is still there. Atmel has gone away. Other players are very small in the market. So the top three is Xilinx, followed by Intel. Altera is Intel now, followed by Lattice. That is who develops FPGAs and sells FPGAs. Yeah, so the internal architecture of the FPGA will just quickly. This is how a FPGA looks like. There is called something called LUTs and flip flops, and there are interconnections between LUTs. These are logic cells. Inside logic cells, there are LUTs and flip flops, or they are called configurable logic blocks. And these logic cells or CLBs, configurable logic blocks, are connected to each other using interconnects, which can be programmed. We have something called DCMs, Digital Clock Manager, inside the FPGA, where you can use build your own clocks for your design. And there are programmable input-output pins or input-output blocks on all the four sides of the FPGA. So you can use whichever pin you want. You can program it as input or output pin and use it as per your requirement. Inside the FPGA, there are block RAMs and there are certain specialized components which are available. Any equation, digital logic equation, will be ultimately implemented on a LUT, which is called lookup table, inside the FPGA. Lookup table is part of this logic cells. So each logic cell will be used to implement certain logic equations of your design. Yeah, this is switch boxes. We'll skip the details of it. Yeah, so this is the flow I wanted to show. This is the FPGA's flow for Xilinx FPGAs, but basically it will hold true for any FPGA or even for ASIC designs. Apart from some ASIC design will have some additional steps, but this other steps are also part of the flow. So how does it work? First, before you start coding into Verilog, before this you have something called a design specification step. So somebody like a system architect or a design architect will first think about developing a new product. Based on the new product, they will decide whether to develop that part. So the design will be partitioned. Some part of your product will be developed as hardware, some part of your product will be developed as software. Now, if you take the hardware section, some part of your product, the hardware part will be implemented as a chip, the other part will be implemented on a PCB, a printed circuit board, using just regular discrete components. So now whatever needs to go on a chip, they will develop the definition for that. That's called a design specification for your design. That design specification is the reference for your Verilog design. So you will write your Verilog design as per the design specification. Once you write your Verilog design, you will have to test it. So you create something called a test bench, also in Verilog. So Verilog is the design is in Verilog, the test bench is in Verilog. The design and the test bench in Verilog will be simulated for functionality. Simulation is a software level verification. So you do that verification step or functionality of your design, whether the functionality of your design matches the design specification given. If it is correct, if it is not correct, it's an iterative process. You keep changing the design or the test bench till we get a simulation result which matches the design specification. At that point, you say my design is functionally verified. Functionally verified means it matches my design specification. So what you do later on, you take the design, only the design, not the test bench, because the testing environment doesn't have to be on the chip. Only the design has to go on the chip. You take the design, which is in Verilog, and you follow this back-end process. The back-end process consists of synthesis, mapping, placement, and routing the design, something called timing, static timing analysis. And finally, we do something called bit file generation. The bit file is a file in the bit format or encrypted format, bits generated, which is equivalent of the Verilog source code that you have written. The same thing gets converted to a bit file, which is then programmed or used to program the FPGA chip on board. This FPGA chip, once programmed, starts acting like the design that you have written. So rest it will act along with the rest of the board. It will start acting as this particular design application on the PCB. This is how Verilog is used in the entire FPGA flow or ASIC flow. Doesn't matter. The same similar flow for all chips. Do you understand this flow, or do you have any questions for this?
I understand the flow.
So this is a big picture view where Verilog will be going into this. And one more thing to understand is this whole step: design, test bench creation, functional simulation. This is all called verification of the design. This is clubbed
Yeah.
under
I
verification.
see a lot of positions, ASIC verification, FPGA verification positions over here.
Yeah, why? Because see, out of the entire design cycle, or let's say it takes 1 year to design a chip completely.
Mm-hmm.
60 to 65% of the time goes into design and verification, which is the front end aspect of design. So till this part, this anything here, this block part goes under front end aspect of design. So the design and verification will take 60 to 65% or even 70% of the entire design cycle. The back-end part, synthesis, mapping, placement, routing, etc., will take the rest 30%. Okay, it's actually the back-end part which
Okay.
is more complex, but that's how it works because the back-end part there is a lot of software. It is done through a lot of softwares. Manual, it's very less manual intervention required in the back-end process. So a lot of backend tools like from Cadence, Synopsys, even Mentor will be used by backend designers, which are called physical designers.
Mm-hmm.
But the front end part, where you do Verilog design, Verilog test bench creation, functional simulation, verification of design, all that is part of front end verification, which will take 60 to 65% of the design time. Since it will take more time, you need more people in those areas. So you'll find, especially in US, you're based in US, lot of even in India nowadays have a lot of verification projects. So verification is where a lot of engineers will get placed into initially at least. Later on, you might go into design and back end part depending on your whatever you feel like doing later on to expand your knowledge.
Yeah. Even I was thinking like getting into verification or testing first because right now I'm in like early stages of my career. Like this is the first job or whatever you can say.
Yeah.
So yeah.
That's a good thing, right? See, I worked on this area for 20 plus years. Slowly, I've moved from
Oh.
I worked in design, I worked in verification, then I worked in only synthesis, and then I worked in only placement and routing and mapping and timing
Okay.
analysis. This is the pure backend part of it. So it depends how you work. Then last few years, I've been working also on embedded systems, where
Mm-hmm.
nowadays I do FPGA design and embedded design on the single board. And then we also develop software. Algorithms are developed on software to do hardware software co-design. Those are areas where you
Mm-hmm.
can expand your knowledge into later on. You have to start somewhere, which is normally this is a good starting point. And then slowly, depending on what you like to do, what you want to expand, where you want to expand your knowledge, then you can progress in those areas. Okay.
Okay.
But this is a general flow that you have to understand. Then you'll understand how Verilog will work and how then later on the whole flow will how this Verilog design will ultimately go and work on a chip side.
Mm-hmm.
Okay, so this is basically yeah, we'll skip the yeah Xilinx FPGA. A lot of different FPGAs. We saw this. Yeah. So I think we'll stop here today. Do you have any questions?
No.
Okay, so we last time we saw overview of digital logics fundamentals. Today we saw number
Mm-hmm.
systems and a little bit of
Mm-hmm.
how why where Verilog or why Verilog is required, where it is used in the overall FPGA design flow. FPGA or chip, how chip design is characterized, PLDs, semi-custom ASIC, full custom ASICs. The PLD, you have FPGAs, microcontrollers, and Verilog, for example, will be used to design FPGAs or semi-custom ASIC or full custom ASIC designs. So Verilog can be used in all the three categories.
Okay.
That's why Verilog is called HDL, Hardware Description Language, which is used
Mm-hmm.
to to design hardware chips. Okay,
Mm-hmm.
so next time we'll start looking at actual Verilog syntax, Verilog language, how Verilog came into how it was designed first of all, how it came into existence and some history, and then then we'll start with the actual syntax of Verilog.
Okay.
So next class today is Friday evening my time. So next class will be Monday evening my time. India time. Same time.
Yeah.
Okay.
And also, like, was the class called off on Wednesday because I didn't get any link or anything?
Yeah, I also didn't get because the guy who schedules the classes, there is somebody else who does this. Was on leave or
Yeah.
something. There was some problem with him, so he didn't send out any link on Wednesday, which I have already informed them to take care of that.
I
So
actually contacted the guy over here. I told him that it's a waste of time for me if you're not scheduling classes.
right,
So yeah, because I already enrolled like a month ago, and
exactly. So I
yeah,
also informed him to be more. So from my side also, I'm allocating time for this training, right? If I allocate time
yeah,
for this training, I don't allocate this time for somebody else or to some other activity. I have to keep
yeah,
this
right.
time free. So it's also wastage for me. So I also let him know. So hopefully going forward, the scheduling won't be a problem.
Yeah, if you can tell him that if he can schedule a little early because I get like invitation links early in the morning at 5:30 or 6.
Yeah. Don't you?
I
I got
I
it.
don't have a confirmation. I don't have a confirmation till the morning, so I have to be like, oh, okay, is the class there or not? I don't know.
I will inform him. It is also good that you send him an email that if you can do it at least 12 hours in advance, for example.
Yeah, 12 hours in advance. Yeah,
That
I'll
will be
send him
good.
an email today.
I have already let him know that 12 hours in advance would be a good time because then you get enough time to prepare for all of this.
Yeah.
Okay, sounds good.
Hmm.
So next class will be on Monday.
Okay.
Okay.
Yeah.
Okay. Yeah. Bye bye. Have a good week.
Yeah, you too. Have a good weekend.